Over to you, sir. You can start the program.
Thank you, Shajit.
Thank you, sir.
Okay. So right now,
Sir, can you press full screen, sir? Sir.
this time full screen. Why? Oh, just he wants. हाँ, ठीक है.
Yes,
Now
sir.
it
Yes,
is
sir. Thank you.
check live. Yeah. Cut shop. ठीक है. Now coming. Okay. Hello. Yeah. So good afternoon, everyone, all the listeners, managers, everybody. So this particular lecture will be on turbulence model. It is, I would say, somewhat difficult subject because till now we do not know how turbulence behaves. Hello. So I was telling you the topic turbulence, which is somewhat difficult topic because most of us do not understand the mechanics, like how turbulence is generated, why turbulence stays, all this. So I will try to share with you whatever I understand. Maybe very limited knowledge, but when you want to compute turbulent flow, some of the behaviors of turbulence have to be simulated. So that was our drive to understand turbulence. But that is not all, that is just a small fraction. So I will try to explain the phenomena and limitation, why turbulent flow is difficult, and whatever the restrictions within which we are computing, and who had developed the models, the linearity viscosity hypothesis, Prandtl's mixing length, and the recent models, K epsilon, K omega, etc. Let's go to the next one is Now, let me first begin with the teachers. So I am remembering those who taught me turbulent flows. Left side top is Professor Rodi, with whom I spent about 8 to 9 years, 9 years. And he is one of the pioneers in the turbulence modeling. Then the right side is Mike Leschner. Mike Leschner is, a great man in turbulence. I once brought him in the country here for lecture and some conference. And Imperial College is from where got graduated and taught there also. And then he went to this Manchester football experts. So there he taught turbulence. I did a full course there with them, Professor Launder and Professor Laschiner. So I actually generated code. Every little step I learned from him. Extremely good. Then left side is below Professor. वो उसको थोड़ा बंद कर दो. Professor Paul Darwin. He is much younger to me, but I have really learned some things from him. When I was at CTR, Center for Turbulence Research, mainly to work with a project for NASA Ames. So that is when I got affiliated with Center for Turbulence Research, that is CTR. But after I left, he also left, I think, within a year. And now he is having his own school at Iowa University. He is having his own school of turbulence. And they're doing a lot of, even including the application of artificial intelligence to understand turbulence. And the fourth one is very well-known face to many of you, late Professor Raddam Narasimha. I'm very sad to say that we have lost him, 2019. He was a genius, no doubt. Actually, all three of them were saying they all consider him to be a guru of turbulence. So Raddam Narasimha was in JNCSR when he retired. Before that, he was in Institute of Science. Then he was director of NL. And it is he who, when I came back from Germany, he almost jumped that you have come, so you should compute turbulent flow. I have no one who can compute turbulent flow. So we are very close actually with Professor Raddam Narasimha. RN we call him in brief. So very unfortunate that 2 years back we lost him, but he has great things done. Turbulence in monsoon prediction and turbulence in our normal engineering cases everywhere. This is very disturbing. Anyway, so with the blessings of all these four people, I somehow entered the field of, I don't say turbulence, it is computing turbulent flows. And that started sometime along with my finishing of PhD, that is 82, 83, like that. So I have been with it for 17 and 21, so 38 years. Nearly 4 decades I have spent in this area. Now, the first question that very much disturbs the scientists, the engineers, everybody, that what is this? What is turbulence? What is transition? Now, I have to go back to the history. In 1885, Professor Osborne Reynolds, you must have heard of him, at Cambridge University, he did this famous dye experiment in his lab and introduced the world to this phenomena of turbulence. So his observation was, once you put the dye slowly and no disturbance, the dye slowly along streamlines propagate. But as soon as you enhance the speed and roughness so that turbulence can generate it, can occur, it was found that the dye goes erratically. It not only mixes, the mixing is erratic. So, and the other thing is, you can still maintain that state of no disturbance if you really have no disturbance inside the experimental rig. Like if there is a vibration of the foundation of the rig, it is disturbance. But if you can make something which is at all no disturbance, then you can maintain that state of peace or calmness, even at high velocity. You can. You are showed also. But the disturbance, now there are two important factors which causes this change of state from laminar to turbulence. These all were his coined out terms. So Reynolds saw that there are two important factors. One is the external disturbance, the magnitude, and another is the fluid viscosity. Right. Now, what does fluid viscosity do? It just, the capability to damp any external disturbance. That means if there is any external disturbance, then viscosity, what it does, it tries to damp that. Right. We know that because in vibration we have read in the spring mass system, if you put a damper there, that means you are putting some viscosity. Then we find the vibration amplitude gets lower, so they damp. So who damps? The viscosity of the fluid. If you put a damper, there will be a fluid in which a small piston moves, and that resolves the disturbance. But it is found in case of flow inside Reynolds pipe that if you give disturbance with a tuning fork kind of thing, then the viscosity of the fluid, it has the capability to damp the disturbance. But how long? When the amplitude of this disturbance is low. Now, if you increase the amplitude of the disturbance, it is high, then actually the inertial forces predominate. That means the disturbance, what you have given to the fluid through the walls, instead of damping, it amplifies. So it keeps growing and don't listen to anybody in a non-linear fashion. So it is beyond prediction as well. How do you say how this nonlinear system will go? But this happens neither instantly nor uniformly. It takes some time and space. Right in the beginning of disturbance, it will not go to turbulence. So slowly it moves. That is called transition. That means, again I'll repeat, because this is the physics. Now, if you have the fluid going through the pipe, you stand there, no disturbance, it is going laminar. It is going in layers. That's in laminae. And now you put a tuning fork or something and hit the pipe a little and leave it. Remove the disturbance. So whatever is gone to the fluid will try to disturb the laminar state. So then you will find motions normal to the mainstream. So we say, hey, it is going to be turbulent. But if the disturbance is low, then viscosity of the fluid, if it is enough to damp it, it will damp. So it will go and dance for some time and then come back to where it was, right? But if the disturbance is beyond some critical, then, and the viscosity is such that beyond that critical, if you disturb, you will see it will not damp, rather it is growing. So that was puzzling even for Osborne Reynolds. What is happening? What is happening is the flow is changing from its laminar to turbulent state. That means it is going to a state which is even not predictable. He said, no, it is not, because when you put the same disturbance now or same disturbance after some time, the nature of the turbulence will be different. So prediction is very, very difficult for that turbulent state. So that is called the fully turbulent state. But it happens. So the dye, what will happen? The dye will mix and you will get a sort of blue, colored water on the exit. So, what really happens? These four sentences I simply took from Professor Launder, who was a colleague of Professor Lashiner, and they really took very good care of me when I was at Manchester. Manchester, you must be knowing from football and all that. So, in the University of Manchester, Professor Launder was a full-fledged big professor, and he was Mike Lashiner was with him. So I spent about 10 days and attended this seminar, or you can say a coursework given by Professor Launder. And that is when I first learned what sort of miracle turbulence can be. It is. So in that lecture, I have taken it from there. The fact of turbulent flow is described in terms of sequence of events. What are they? At moderate Reynolds number, the restraining of the disturbance is done by viscosity. Now, if the restrainings are too weak to prevent small random disturbances in a shear flow from amplifying. Shear flow, any boundary layer flow is shear flow because you have a shear stress there due to wall presence. So the question of turbulence is whether the disturbance is dying or it is amplifying. So at certain Reynolds number, Reynolds observed, I call it Reynolds number, Reynolds himself observed that the disturbances start amplifying. They grow, they become nonlinear. There is no rule. They interact with neighboring disturbances. So one disturbance will go part into several small bubbles sort of, and then they will interact and somewhere it will be a bigger, somewhere it will be a smaller, like that the whole fluid is disturbed. And violating any rule, neither of laminar flow nor of anything. And vortices, those are formed. It is better to use that term because vorticity is something we can represent mathematically. So better to say the vorticity increases. And the mutual interaction leads to a tangling of vorticity filaments. So one vorticity filament, two, three, four, they tangle like two vorticity filament, they merge and be a bigger one. Sometimes they go to smaller one. And eventually the flow reaches a chaotic, non-repeating form. This is an amazing thing, describable only in statistical terms. So you have to accept this is something we are making a futile attempt as mathematician alone because we are seeing what happens. You can see the grid turbulence. You put a grid in the left and allow the water to go. You will see up to certain distance, they go like a laminar flow. And after some time, they mix up like anything. This is a hell, chaos. And if you put aluminum sprinkle on the surface, you will see the sprinkles distribute like that, which has no head or tail. You cannot predict this with any mathematics. So it goes beyond physics and mathematics. But it happens. If you see the smoke from a chimney, for the first few feet or maybe centimeter, it is behaves like a laminar flow. That means slowly they in layers they go. But after some time, whether there is atmosphere disturbance or not, they simply go like this. So they're like small vortices in different size and different strength. Remember, different size, different strength. And the assemble of that is coming out. So who is there to predict this? So that was the stage when Reynolds even raised his hand that, well, gentlemen, this is going to a chaotic situation. But what the scientists could finally reach is yes, they go, but they are still assemblage of vortices of different size and different strength, right? And that assemblage is displaying the turbulent flow level. So when you want to model mathematically this kind of phenomena, it is too tough. That is why even in the last 200 years, nothing much has taken place. Attempts are going. Level of reality. So it concerns the scale of reality considered. Like in molecular level, we don't use Navier-Stokes. We use, in the molecular level, we use Boltzmann equations, right? But you can come to continuum level when the theory of continuum is valid, the fluid mechanicist define it. Then we say it is Navier-Stokes equation for Newtonian fluid. But does Newtonian fluid behave like Newtonian in turbulence? No. So the order and the cosmos of the flow is lost. So these are the level of reality. We don't know where to place turbulent flow. The other is the level of space-time resolution. The space scale characteristic, time scale characteristic, how the system evolves. If there is a big vortex, do they divide itself into small vortices? Or is it that at some place they divide, at some place the small vortices coalesce to form big vortices? So both are possible. So uncertainty. The third one is the level of dynamics. So how do we describe the dynamics of flow? We describe usually by the relative importance of the forces. Like when the viscous forces are dominant, present, and they try to damp disturbances in different places, and pressure force is there, and inertia is there. We call it Navier-Stokes equations because they very nicely describe the mathematics or physics of laminar flow. And then if the viscous effect is too small, then we say, well, my pressure and say to find the effect of bends and all, Euler equation is sufficient. Then I don't need to consider the viscous effect. They are small. If the both are small, I mean, we can go to potential flow. So potential flow, of course, pressure forces will come out, is that means this is satisfying Laplace equation. That is, even my viscous forces are gone and everything is gone. What I'm left with is the Laplace equation. Just by simple potential phi, I can describe the flow. What do you want? If you want velocity, you differentiate with respect to x or the potential, you get the x direction velocity. So it is more like a electrodynamics thing, like electrostatics thing. Now the question is, how do we say when it goes to laminar and Laplace equation, no question, everything is defined. But when I'm going to the turbulence stage, everything is moving. This was done by P. Sagoy, who is very well-known man. The energy spectrum with the wave number, and it is found what is getting total in case the velocity and dimensions are such that there is nothing left with like this, the whole thing is modeled. This is called the steady Reynolds average Navier-Stokes. So everything is there, but I am not considering anything. I am saying, okay, I will do averaged model, RANS. That is steady RANS. Sometimes a small portion, like you see the peak here, that within that uh, spectrum number of K, energy spectrum, we are resolving. That means we are solving the velocity field as a function of pressure and temperature and everything. Time mainly. Because K is the frequency, so time. And then the rest of the thing, what is there, is modeled. So I'm not doing any justice to that part. I'm saying it is model. Model means what? Nothing. But I'm resolving the small part. This is called the unsteady Reynolds average. That means some portions which are a function of time, only some portion which are not in the level of turbulence, I am resolving, like flow behind the cylinder. I have some time-dependent functions. Then the third level is large area simulation. That means what I'm doing, I am reducing the grid size. Enough, till the level when at some level I have to leave it. So up to reaching this K, I am having fine and fine grid. So I can resolve the left part, okay, very easily. That means I am simulating the large eddies. But beyond this value, that means my beyond the grid size, I don't have, so I have to model. So the small scales are modeled, but large scales are dissolved. So I simulate the large eddies, small eddies I model, right? I don't allow them to play the interaction. Excellent book, Sagar's book, you should all read, LES for incompressible flows. So this can definitely say up to what length you can go. And if you do direct simulation, that means you are promising to the user that from the lowest to the highest, every vertical behavior I will capture with my resolution of time and resolution of space. Okay. So next one is, no, what was the next? Yeah, left one. Not, what is the next? Take it. Okay. No, that was before this. Yeah. Now, what are the major fields? Now, from this point, you will see I am not telling you much about the theoretical part. Not that it is not happening, it is happening, but I am too poor a person to say about the physics of turbulent flow because for the last, say, 1890 was the Reynolds identification of turbulence. So you can imagine how many years are gone. So 1.5 century is gone, but still we cannot resolve. Various methods have been tried. Fractal was tried, spectrum equation was tried. Every method is tried, but nothing. So, but observation is a lot. I think the experimental people have seen a lot of things in turbulent flow. I hope you understand with me the randomness. That means the smoke which is coming out of the chimney, there is no guarantee to go from a particular stream. And next minute it can go the other way. So everything is depending on time, depending on location, depending on space. So highly random. And as the mathematicians say, random phenomena is always difficult to analyze. There are methods, but how much is the confidence? Irregular with wide range of scales. Like you'll have very small vortices, you'll have very large vortices. That is the scale, the size. You can have very strong vortices, you can have very weak vortices. That is the velocity, the strength, the omega, the rotational strength. So rotational strength, even if it is a small, if it is very strong, it can capture, it can spoil the field there. So all turbulent flow are unsteady. If somebody presents steady turbulent flow analysis, you can throw it away because it does not happen. No turbulent flow is steady. So unsteady and three-dimensional. I have seen even one-dimensional assessment of turbulent flow. I don't know what that means because turbulent process is mixing intensive with high exchange rates. It is unsteady and three-dimensional. Absolutely clear, and all the pioneers will agree. It's a non-linear process due to advection. That means your U and V together is creating this. Maybe U dash is the fluctuation in U and V dash is fluctuation in V. Now there is a cross component U dash V dash bar. So because the two fluctuation in two directions, that pair is generating turbulence. Due to advection, that is our convection. Correlation is responsible for energy exchange between different, but the question is, will it stay like that? Not, predictable. No, viscosity plays a role. If you put a plate there, as you come closer to the plate, the viscosity becomes dominant, the laminar viscosity. So all this vertical process, mixing process, will be shut down. And when you come very close to the wall, it becomes laminar again. Next is rotational character. Obviously, because what is turbulence consist of? Multiple vortex elements of different size and strength. Please remember, all of you, this line. Turbulence is behaving or exhibiting itself as an agglomeration of multiple vortex elements. Chota vortex, bada vortex. Strong vortex, weak vortex. Everything. And they are maintained by the kinetic. This is very important. That what about the energy consideration? I cannot just make it go fast or slow without supplying anything. No, who says? It is supplied from the main flow. If you see the equations, it is very clear that the energy which is going into turbulence kinetic energy, it has with the same quantity with a minus sign in the main flow equation. So that means whatever you are seeing, this tamasha of the rotational character, it is all tapped from the main flow. So it cannot be infinite. After some time, it damps down due to presence of the bodies. So that is dissipation, dissipative nature. So turbulence is generally damped by the fluid viscosity. So if you are away from the wall, the viscosity effect is less. When you are close to the wall, the viscosity effect will be stronger. So viscous forces effective on the smallest eddies near the wall eventually transform the kinetic energy of the turbulent motion into internal energy, heat, right? So these are the major features. Now they go back to the mathematician and ask him, sir, you answer this question of turbulence. We have continuity equation in a 3D. J varies 1, 2, 3. So that is continuity. The momentum equation, again, below this, the unsteady plus the convective term, pressure and viscous. Everything is written. So there are 4 equations. And there are 4 unknowns, U1, U2, U3, and P. Assume incompressible flow. Density is constant, mu is constant. Then where does it stop? Mathematicians say, of course you can solve it. Because momentum equation, there are 3. U1, U2, U3. And continuity 1. So 4. So 4 equations, 4 unknowns. U1, U2, U3, P. So it's a closed set. So they have no trouble. But you have to see that the eddy size, which is displayed in the flow, may vary from d by Re to the power 0.75 to d. If your dimension characteristic pipe diameter, you can have a vortex of the diameter of the pipe, you can have a vortex of, suppose Re is 10 to the power 6, then you can d by 10,000. So now imagine the flow picture. It is agglomeration of vortices of different strength, which have a very wide range of variation, and of different size, which is also wide range of variation. So the problem is how to resolve this wide range of time and length scale. Because you will have prohibitive, disk space required and computation time. Like a simple channel flow, turbulent channel flow at R is equal to 10 million, 1 million, may need billions of grid points because you have to resolve those small vortices. So I'll have billions of grid points and perhaps millions of time steps. And this may take even years of computational time to just solve on a modern supercomputer. See, like Cray, XMP and all. It can take years of time. So today you put the job, after a few years you will get the answer. If you want to do turbulent flow at 10 to the power 6, obviously that is, something impossible. Who will wait for that time? Engineers won't. So people started finding out what are the ways to capture, if not the turbulent characteristic, the effect it is pulling on, putting on the mean flow characteristic. Go to the next one. I hope you are equally uncertain about turbulence and equally certain about what I am saying. Good. Now, there are different approaches, obviously, which will take years of computation time. Who bothers? Who cares? No one. So, methodologies used is direct numerical simulation. Here, of course, we say, okay, we are going down to the computer. That means I will have no model. But then what guarantee should be given to get the right answer? I have to resolve the time scale up to that 10 to the power minus 6, minus 7 level. I have to get the grid also up to that level. So God knows what the timing will be, timing of computation. So this is direct numerical simulation. Up till now, whatever petaflops we have not yet been able to solve everything. Some problems where the effects are less in the lower range, we have solved. Next is large eddy simulation. What is that? That is, you do your gridding so fine that you can reach as minimum as possible. Well, if it is 1 micrometer, fine. So let your grid size be 1 micrometer. That means you are approaching DNS, but still the eddies which are below that 1 micrometer size will still play a role which you are not simulating. So what you are simulating is the large eddies, and the smaller eddies are still to be modeled, right? So that is another approach. It's in between RANS and DNS. And third is RANS, which we do, Reynolds average Navier-Stokes. This is, you are trying to model the effects which the turbulence leave on the main flow. You are trying to model the effects what the turbulence, of course there are assumptions. That's why we call it model. That is not exactly what turbulence is creating on the main flow, because main flow is also affecting turbulence. So it's a complex phenomenon. Other one is the Reynolds stress transport equation based model. This is something in between RANS and large eddy, because here the effects are mathematically first established by other scientists, and then we try to find out the not audible. Why is there? You let somebody sleep. Ah. So these are the methodologies which I have said. Of course, now many other things are tried, like from a lot of experimental data which has been accumulated, people are trying the artificial intelligence techniques, right, to find out if there is any law which controls or which speaks about turbulence. I'm going to give a lecture on that topic sometime in a forum, but that's a very different approach, AI approach. Okay, using the DNA and ANA and all those schemes. Like data science theory help to understand turbulence. They are approaching that because a lot of experimental data are available now, and that too in the cloud. So you can pull it down and try to see if there any law exists. And what are the desirable features of a model? If you want to mathematically model turbulent flow, first of all, it should be a great width of applicability. You can't say, oh, this flow it will work, that flow it will not work. No. With a range, big range. Then accuracy, how accurate your, so that is only comparing to measurement. Then engineers will always prefer, please make it mathematically simple. They don't want to get into very complex mathematics. Then this should be computationally stable, because I can only do that analysis using digital computers. Analog doesn't work. So digital computers have limitations of round-off error. So I have to think of that, am I getting a computationally stable solution? Otherwise, no conclusion about physics will be correct. Then next. This is a good slide, in my opinion. I have only made it, but I find it good to explain. See, left side, what you see is a stationary flow. That means there is a flow happening in a pipe, say, or a channel, and somewhere inside that you put a probe, say a hot air anemometer, that is a good probe, and simply connect it to the recorder and allow the flow to go for some time. What you will observe in the recorder, the say phi is okay, velocity, streamwise velocity. You will see the streamwise velocity will be recorded as some fluctuations. No? Have you seen the picture on the left as fluctuations? Now the question is, why? I'm giving it at an average velocity. Why does it fluctuate? Yes, the cause is turbulence. Cause is turbulence. So can I say at any point of time t, the velocity or anything, pressure, any flow variable, consists of two parts. One is if you take a time average of this, that is your average, and another is the fluctuating part. So what is the average definition? 1 by t, there is a period after which it repeats, 0 to t phi dt, t tending to infinity. Right. So that's the theoretical definition of pi bar. That means what we average or mean we measure is this pi bar. Phi can be pressure, phi can be velocity component, phi can be anything. Again, there is another concept of this is not different, this is another kind of flow where there is some unsteadiness due to the flow itself, like flow behind a cylinder. Flow behind a cylinder beyond a Reynolds number, the flow itself is, even laminar flow is unsteady. So those cases, non-stationary flow. The flow, basic mean flow is a function of time. But if that is laminar, then it will simply go according to that. But if it is turbulent, then basically around that there are fluctuations. You can see small ups and downs. So here the time scales are the time averaged plus the coherent. You can see time average is the same. Coherent is this, the phi tilde, and phi within bracket, that is ensemble averaged. That means the fluctuation of the stochastic remains the same. But because the mean flow itself is varying with time, so around that is the stochastic. So this is the turbulence part. The left two things, time average and coherent, is ensemble averaged. It's a French word, ensemble. So that ensemble averaged is something we can measure with a tube or something. So in turbulent flow, where the mean flow itself is a function of time, like flow behind a black body. And the small phi is the turbulence effect, right? So whether it is steady flow or it is unsteady flow, we have the effect of turbulence prominently observed in experimental finding. Good. Next. These are very important, the development of the models. Yes. Now we come to very interesting. So Reynolds already decomposed this. We call it Reynolds averaging, right? So it says instantaneously what you get, maybe from a probe, there is response. That is a time average plus the turbulent. So the turbulent part is a part of the, it is a function of time, and the time averaged is what you average over as bit time. So if we now use this decomposition for velocity, then the first term of the Reynolds equation, Navier-Stokes equation, del T of rho ui, which means ui bar plus ui, small ui, fluctuation. And if we take average, it will be simply del T of rho ui average, because the small ui, which is a function of, which is a function of time, will go to zero because it is a periodic sort of thing. So we find in the first term, there is no other contribution, only the local velocity will be replaced by the time average velocity, right? So turbulence does not cause anything in this component. The second part is del del xi of rho ui uj, product of two velocities. Now, both the product will have turbulence component like fluctuation. So I write simply replace. I have intentionally done it in a clearer way so that everything will be clear. Now, this will consist of four terms. So there are four terms here. The first term is more or less equivalent to my laminar case, only the velocities are replaced by the time average velocity. Now, second term ui bar u will be 0 because when I time average this, the ui bar goes out and ui time average is 0. Similarly for the second term, third term. The fourth term, not known. Fourth term is the time average of the fluctuating product of the fluctuating velocity. I can give you an example. Suppose you small ui and small uj are sine function, sine omega t. So then this will be sine square omega t. Now if you make 0 to capital T, sine square omega t dt, this will never be 0. You can make 2 half, then 1 minus, so it will stay non-zero. That means even if I time average, I am getting some extra term generated from the definition itself. Even if I use ui plus ui, no other higher order terms, I am getting one extra term. That means the stresses that will drive the velocity, momentum, are different. In laminar, this is 0, and in turbulent, it is coming. See? So now I say this del del xj of minus rho ij bar is a Reynolds stress. That means in the balance of momentum transport, now in turbulent laminar flow, I don't have this term. But in turbulent flow, I have this tensor, Reynolds stress tensor, which is nothing but the time average of the fluctuating components, U1 square bar, U1 U2 bar, U1 U3 bar, like that, U2 square bar. There are 9 components. So this whole tensor of 9 components is the mathematical effect of turbulence. Of course, under the assumption that what Reynolds did, and I assume the function is like this. Similarly, if you go to heat transfer, the laminar flow heat transfer equation was up to this, Fj bar. But because the velocity and the temperature will also have a correlation, so I have rho uj phi bar. So this is the turbulence transport of heat. Scalar means it can be heat, it can be mass, can be anything. So the what the turbulence model want to do, it is now deciding its purpose. What am I going to do with all this? We are trying to find, the people tried to find out what is the magnitude of uh, quantum of value created from this tensor or from this turbulence scalar tensor. Then it will affect the momentum equation, it will affect the scalar transport equation. But how do I do that? I mean, how do I find out the ui uj bar? That is the thing which is causing some extra stresses, and hence the flow, the temperature distribution, heat transfer, everything is affected. Now, this is called the Reynolds averaging, which I showed, the mathematical. But turbulence is a state of fluid motion governed by dynamical laws. That is already said, Navier-Stokes. And the challenge of description lies in the complexity. It is so complex. See, look at this and look at this. The true image of the jet coming out and the true image of a plume coming out after atomic explosion probably. So you see the curliness all along. Now, when I do Reynolds averaging, is it not going to feel this? Is it not going to feel the other one? So what is happening? A lot of dynamics is left into the water. Massive loss of information. Why? Because you are Reynolds averaging. So till date, whatever modeling of turbulence we do is this. That is why some great man from an United States famous university told what you are doing is turbulence muddling. It is not modeling. Muddling means you are just playing with mud. Correct. So here, what is the way out? You refine the spatial grid, the temporal grid, do it for a smaller and smaller, then your losses will be less. At least some part you can manage. So that is the subgrid scale, and the effects are to be modeled. That means if you do large area simulation, you can do this, but at the same time, the effect of the turbulence must come from the subgrid scale. But we don't do that in Reynolds averaging. So the Reynolds average model are always producing this. Good. So what are the classification of turbulence models? I mean, whatever we have done up till now shows that there is an effect, but we are unable to capture it, right? Theory, not experiment. Experiment, there are other methods. So three kinds of thing I have written. First is the linear eddy viscosity based models. Now you will ask me what is linear eddy viscosity? I will come to that. Some hypothesis. Based on that, we can make different kinds, levels of model. One is zero equation model, where I will say that let me show you the linear eddy viscosity. Go to the next one, and then I will come back to this. No, no, after this, because before this is not there. No, no. Where is the Boussinesq hypothesis? It must be before this. This is K omega. Boussinesq hypothesis will be before this. Why have we thrown it out? Oh, this is two equation. Before this. This is also two equation. Before. No, this is repeating. Oh, or again. I mean back. This is going front. Oh, go up, 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 up. Where is the linear eddy viscosity model? Oh, Manas maybe. Anyway, I will come to that, but I am not getting in the. No, these are all based on linear eddy viscosity. But definition कहाँ गया? और आगे back. I'm sorry, I find it out. Just wait for a minute. I'm getting it. I'm not getting it now. One slide is missing. No, not that back. Can I? Oh, you are in the lecture 3 only. Then it should be here. By mistake. It will be a problem. No, I cannot explain that. So, no, it is there. Come out of this. Here you won't get. No, these are going other direction. What we are showing now is 3. Come out of this. No, you can close and come out, then we'll see. Nur Alam. I'm sorry, little few seconds I will take. And it's yes. So now let me explain this linear eddy viscosity hypothesis. The question is, why do we need all this? Because nobody could say this is a random process. So people were trying to look at the atomic theory because there also the molecules are moving like the turbulent flow particles. So here, Boussinesq was a French guy, and you can see the year 1877. So more than 150 years back. The analogy was brought between the random process of turbulent transport and molecular transport. Molecular transport in laminar flow, and we want to see whether the turbulent transport also behaves in the same way. So you can see in molecular transport, we know the shear stress is mu times the laminar viscosity times the mean strain rate minus some two-third mu. This goes off because the divergence of velocity is zero. And in turbulent transport, our interest is to find out the rho ui uj bar, which is dimensionally somewhat equivalent to, but rates are much higher because it is turbulent. So the argument was, why not we put here something of the dimension of viscosity? But this has nothing to do with the viscosity, that you should understand. So dimension of viscosity, and then instead of the mean strain rate with local mean, local values, we put the time average values of ui and uj. Otherwise, same. And here we put two-third rho k delta ij. So the Kronecker takes care of the fact that I equal to j, it is there, otherwise not there. So this is structurally same like molecular transport. But what is different between the two is there is also something similar to Reynolds stress, shear stress. It is mu t. So mu t has the dimension of the laminar viscosity. But it is not viscosity. It is not a physical fluid property. It is the local turbulent property. So you can imagine the depth of thought of Boussinesq. And he thought that then some dimensionally this will also have a viscosity dimension. So you can see the laminar, the mu is what? Density into the mean free path into the molecular velocity, usually. Right? So mean free path is the movement of the molecules. Here we are thinking in turbulent flow also, it is not the molecules, but it is the chunk of fluids. They are moving and mixing. So similar to laminar, we said length scale that will be decided by when the heating takes place. One identified heating, then the second identified heating. How much length it has covered. And the velocity with which it moved is velocity scale. So dimensionally, it is exactly this, that density, that's why we call it the name viscosity. But it is not viscosity. Viscous forces have nothing to do with it. No, go to the page. Better. Why it is coming again? Oh, we have to come out of this. So if we see that, then we can find out the turbulent viscosity also, or the eddy viscosity. That means that is happening at a different scale. Similar process, heating of the molecules, but not molecule, they're chunks. This length scale is turbulent chunks are moving, and that is causing the turbulent stresses. Like the mean free path traversed and the molecular velocity was creating, getting the laminar viscosity. So, in understanding the turbulence effect of turbulence, it is only mu t, that is eddy viscosity, which is a hypothetical because there is nothing you can measure as eddy viscosity. But it speaks of the local turbulent property. It varies from different place to place. It is not like a physical fluid property. And if we know that, then we can assess the magnitude of the Reynolds stresses, which is affecting the mean momentum transport in the turbulent flow. So we have to go back to where we were. Or you can put it afterwards. So now, after describing that, I'm coming back to the methods which are used to get those. I'm sorry about the disturbance, but somehow one slide was dropped. I will include it. No, this is okay. Okay. This was in the first. So it was over here. This is okay. I will say Well, this was the first, second. No, that was the first one. First. No, where we were. Lecture 3. Next one. You can get it. No, it's not there. Yeah. Okay. So there one thing was missing, we have given it. Yes. Go down. Go down. Go down. So, no, before. No. So based on this eddy viscosity concept, people started thinking that can we simulate turbulence similarly as the molecular motion was simulated. So this Boussinesq concept was used. Now you can see based on linear eddy viscosity, that is called the LEVM, the linear eddy viscosity based models. So zero equation model means whatever we have shown, the turbulence length scale and velocity scale, both we have to prescribe because you are not solving an equation separately for them. One equation model means one transport equation will be solved for the velocity scale. What is the best thing to do? Velocity scale can be square root of turbulence kinetic energy. So if we can frame an equation, but only thing you should clearly understand, these equations are not the sense in which mathematicians will call it equation. This is something like, your coupling, or you are collecting terms from different places and getting it justified by the physics, the reasonings of physics, and call it an equation. So nothing can be, this cannot be derived. Only K equation can be derived, others are not. So this transport equation for the velocity scale and length scale. One equation model means the velocity scale will be solved in a transport equation and length scale will be prescribed. You can take out any empirical relation to get the length scale. And two equation model means there will be two transport equations solved, one for the velocity scale, one for the length scale. What it will be, it is varying from model to model. The non-linear one I will not discuss because this is not assuming the linear eddy viscosity hypothesis. It just modifies that with some non-linear terms, higher order terms. So, but people have done successfully with some cases, difficult for coding. Then the Reynolds stress transport equation based, This is very good because this is originally it derives the Reynolds stress transport equation. So for each of the Reynolds stress components, there will be six components, three, three, six, nine total, but six will be, I mean, they will not be there, symmetric. So because it is symmetric, so I will have one, two, three, four, five, six. So the six transport equation will be solved for six component. I will solve for transport equation for u dash square bar, for v dash square bar, for u dash v dash bar, like that. Six. And then from there, I'll find out the eddy viscosity effect, the effect of the eddy viscosity. It's a very complex model. Rohde was the first man to publish this, with whom I worked for 8 years. And we'll not go into that. In the meanwhile, I think one person was very important, that is none other than the another engineer. He was also a mechanical engineer, but more a physicist, Ludwig Prandtl. So Prandtl argued, yes, I understand that, but if you really say there is something like eddy viscosity based on the theory of molecular theory, then why don't we say this eddy viscosity is low dimensionally correct and the velocity scale is du dy because mean velocity gradient can always be measured in his Göttingen laboratory. So velocity scale, and here dimensionally we can see it needs a length scale square. Now the question is what the length scale should be, but we should not forget that was 1925 when Prandtl was thinking that this is a very good idea to compare these two, the molecular motion and the turbulent fluid motion, saying that one is just a scaled up version, but the mechanism is same. So then there we have some mean free path. Here we should have some mixing length. It's much bigger than the mean free path. So what he did, he was an experimentalist basically more, but he has, I mean, discovered theory without which the aircrafts could never fly. Such a great man. So cylinder, on the wake of the cylinder, the mixing layer of two fluids, then a circular jet orifice, then a pipe flow or a channel flow. Everywhere he said this is true. So his idea was that this mixing line will be proportional to some characteristic thickness. You can see the deltas are shown here. In case of mixing layer, this is the delta. In case of flow past, far away, this is the 2 delta. Half of this is delta. In a boundary layer, the boundary layer thickness is delta. So like that, we have, measured the stresses and then found out what should be the correct value of the alpha. So you can see Farwick here said, if you take alpha equal to 0.18, then the measurement values compare well with the theory, his theory, mixing length theory. But the problem was, in my book it is detailed, reasonably good for thin shear. These are thin shear flows. Thin shear, the shear flow is caused because of two fluids with two different velocity. That's why the shear region. But they are different. See, if you compare the velocity distributions of a mixing layer, you need an alpha of 0.071 here. If you do round jet, it comes 0.08. If you do far away, it is 0.18. So it is widely varying, very widely varying. So, but the good thing is, if you do it for simple cases, many of the boundary layer flow, like mixing layer, where the thickness of the layer is less, we could get reasonably good values. But provided you will believe to this, but simplicity is right, computation economy is also right, but it is insufficient generality. You cannot say if I have a bend here, what to do. So difficult prescription of mixing length. If you prescribe correct mixing length, then L into D is correct, velocity scale. But how to know this? So many cases were done, but experiment was successful. But when you try to generalize, it fails. And then we go to the next one. This was something on the boundary layers that when we are trying to get a turbulent boundary layer, this is the wall surface. So Prandtl has very clearly shown, and later on other his colleagues also, that this total boundary layer thickness has three different regimes. One is the sublayer where it is purely laminar. Here there is no confusion because your U plus, what is U plus? U by shear stress velocity, U tau. So U by U tau is U plus and Y plus is something like a Reynolds number based on skin friction velocity. So Y U tau by nu is Y plus. And it has very clearly been observed in experiment that U plus equal to Y plus is valid. It is obviously valid because laminar. There is no uncertainty about turbulence. So up to around 10, 11, we can follow this formula and then we can get that U plus equal to Y plus is good. Then actual layer which is coming in between. So this is the boundary layer formed here. I mean, plate is vertical. On that, the wind is flowing from bottom to top. And you are seeing the boundary layer across the boundary layer, how the Y plus and U plus varying. Now we saw that up to 10 of Y plus, it is a laminar part of the boundary layer because near the wall. It goes very well following this. But in the turbulent part, it goes linear on a log-log scale. But we don't know what law is following this. So that is what is called the logarithmic law of the wall. You can see U plus equal to, if we don't write Y plus, we write 1 by kappa log EY plus. That is 1 by kappa log Y plus B. So both von Karman and Prandtl worked a lot on this to find all these points, many points, and came to this law. This is called the logarithmic law of wall. So inside the boundary layer, the first one will be the sublayer near the wall. Then there will be up to say around 1000, there will be a log layer where this follows this logarithmic law. But after that, there is a wake or defect layer because where it is mixing with the main free stream, there will be another defect layer. And there it does not follow the logarithmic law. You can see it is defected. So if we use log law, it is okay up to certain value of Y plus. If as long as my grid is so fine that I have resolved up to this Y plus. Then so keeping that in mind, the two equation model was proposed by Jones Launder, later on by Launder and Spalding. It is probably, according to Stanford competition, the simplest complete model of turbulence. I don't know whether how justified it will be to say complete. Is more or less the foundation for most of the turbulence model research during the last 30, 40 years. So here the argument is, for the length scale, you solve for another equation. For the velocity scale, the strength of the turbulent vortices, you can use K, square root of K. K is the turbulence kinetic energy. It is actually eaten up from the mean flow, but we have a root over K, and root over K is the velocity scale, and you can frame an equation. But I am again saying this equation is not exactly derived. It is framed from the concepts that this part will be this part will be the viscous part, this part will be the work done part, generation part, this will be the dissipation part. So it is, I can say, the physicist's concept to bring it into the form of an equation. So nobody should try to derive some equation for epsilon. It will not happen actually. And what is epsilon? Epsilon is the dissipation, because turbulence ultimately, when it comes near the wall, it is dissipated due to viscosity. So epsilon is the relevant turbulence dissipation, and the length scale is, by dimensional reasoning, is that k to the power 3 by 2 by epsilon. And these two equations were proposed by Launder and Jones, which was this, and then we can say the eddy viscosity, which is the only thing which is affecting the mean flow equations, transport equations are rho c mu k square by epsilon. So this is the kind of effect of turbulence on the flow, right? So it is a good compromise between universality and economy. This is my sentence anyway, for engineering problems. Needs, the question is, if you use this tool away from the wall, it is fine. It more or less observes follows the physical measurement data. But when you come close to the wall, we have to do something. So near wall modification, because it is insensitive to the free stream boundary condition. That is also another thing. So near the free stream, something is going wrong with this, and near the wall, something is going wrong. And poor performance for flows, actually they made a Stanford Olympics. I also sent some result if I remember, 1981. So unfortunately, Peter Bradshaw has to finally from Stanford raise his hand saying not possible. Separated flows or non-separated flows, everywhere they collected data from all over the world. But it was very clearly shown that the performance of this kind of model is poor, especially if the change of strain rate is more, like curvature is there. For a simple flat plate, it might work well. But when swirl is there, rotation is there, or flow has separated, then it doesn't work very well. Now the question is, what is epsilon? You can see here, the length scale is deciding the epsilon, the dissipation. How the kinetic energy of turbulence getting dissipated near the wall. So next one. Then Wilcox came in the picture sometimes in 93. He said K equation is fine, but don't use epsilon, use epsilon by K, which is omega. K by, you can see here, instead of K square by epsilon, we have written K by omega. That means it is the vorticity he think is a better thing because always the fluid mechanicists have understood different kind of flow patterns through vorticity. So I said, why don't you say this is a turbulent vorticity? And you write an equation for this. Exactly like epsilon, just change the dimension, the scale definition of vorticity and epsilon. And this equation is valid in the laminar sublayer and near wall modification not needed because you can find the value of the omega right on the wall, possible. So, but the difficulty with the K omega model is when you are going away from the wall near the free stream, it doesn't work well. So the definition loses its significance, and near the free stream, epsilon is better, much better, whereas omega is very good for near wall. So these two are combined by Mentor, who is an ANSYS guru. Go to the next one. I don't think that's so. Here, first, before going to Mentor, I wanted to say what is the effect of the wall, because all these are derived without wall. Now, if the wall is there, the first thing is the viscosity diffuses vorticity and damps. So the viscous diffusion terms become the largest term. That means we have to do something special to allow the Nénot stress transport to go near the wall. So the inviscid, so this is one effect, the viscous effect, which is diffusing the vorticity. Another effect is the inviscid blocking, even if it is not viscous flow, if you put a wall and the flow is there, the component normal to the wall automatically having a stagnation sort of effect. It is hitting the wall normal to it. So that's why the fluctuation in a direction normal to the plate is automatically dissipated. How to take care of that? So what they do, they modify the equations near the wall. So you go and yes. So you can see control volume. This is parallel to the wall and put some law there. So what is done is logarithmic law is Vp. Kinetic energy at P is fine. u tau, and tau w, that is the wall shear minus lambda. And what he in the substitution, he has already inside the equation put lambda w to be mu by delta n, because normally tau is known as mu vp by mu dy. And if this point P is away from the laminar layer, you use the same thing, that is fully turbulent layer. So while computing the analysis, we have to take care of this statement. That means if the first point is away from the sublayer, use this formula. If you have a fine grid, only this point comes close, you use this. But this is for a zero pressure gradient flow and computation will be easy. But we do not know how good it is for non-zero pressure gradient. So there is a question mark. So I told you this model is self-healing. You have to keep like this. This is another way of handling the near wall. There is some law which Patel, Rodi, they proposed, that your turbulence cannot be used from measurement we get near the wall. Say 4 point, axis about 10, whereas the eddy viscosity profile for channel flow. So here what they do, they use the exponential function to damp the eddy viscosity, because right near the wall it will be damped. And then you can find out, and a very near wall resolution should be quite fine. Then we get this kind of variation which matches with the measurement data. DNS, you can have DNS here. Good. So next one. Now, usually the user will first ask, what are the boundary conditions we'll use for the scalars like K, epsilon? The first thing is the K can be taken as some function into kinetic energy, mean kinetic energy. Well, what its epsilon F1 will be depends on problem to problem. So this is a sort of empirical guess. And omega and epsilon, one can find out from the level of the viscosity, which is the laminar viscosity. You can multiply by F2 and get the mu T in. And these F1, F2, they depend on the free stream turbulence level. I mean, hopefully that will be known, the measured value of the free stream turbulence level. And in the outflow, of course, stream derivative 0. For any variable, you do that. On symmetry, normal derivatives are 0. That is also always we do, nothing to do with near wall. And wall, of course, if it is k epsilon, we will try to put the value of the wall at epsilon as 2 nu k. This is the limiting value. When close to the wall, it follows this law. So, and omega at wall, it can be reduced because this is directly from derivation. So you can put 6 nu by c omega 2 y squared. So if the grid is known, you can find exactly what the omega wall should be. This is something which was proposed by Mentor, who is a great man with ANSYS. He is the main man behind ANSYS's new models. And here he argued, this one you can remove it, that why the k omega doesn't work well near the free stream and why k epsilon does not near the. So these two failures. One is over prediction of the shear stress in adverse pressure gradient boundary layers. He says, although we know the formula near the boundary layer, but we miserably fail when the adverse pressure gradient case. Remedy is impose a bound. So don't allow the Reynolds stress to go the formula. Between the Reynolds stress and K, whichever is less, you put that value of K. If the Reynolds stress is less than K, you put that. And the spurious sensitivity of the free stream, that is for the omega. So near the wall, definitely use the K omega model. And near the free stream, use the K epsilon. How will you shift? He has given, I am not going into the detail of the mathematics because this is simple, one can read. It's empirical, there is no deduction for this. And if you use this, suggestions of Mentor, we get that near the wall, it follows the K omega model, which is valid and which is very true, where near the free stream, it follows the K epsilon model, which is much better than K omega model. So it's a very judicious application of K epsilon and K omega. And I think it has done a very good job without any experimental data to match. Go. Oh, we have a journey. Non-linear, of course, the weakness of Boussinesq is it cannot capture the normal stress anisotropy. The normal stresses differ in directions, so that cannot be captured. The insufficient sensitivity to the mean strain rate. Some problems with a high change in the mean strain rate, it was found whatever you do with the model, it doesn't change the results. Then turbulence generation at the impingement kind of zones. This is very dangerous. So one need to give some limiting value. That's what is done. And violation of realizability, I'm not going into that detail because to understand this physically and mathematically, one need to go further into the K model, details of the K. Then second moment closure gives a superior foundation, but why reluctance? Why people don't want? That it is available in all the commercial codes, but people say no, because very more algorithmic complexity, numerical challenges, you run it after 100 iterations, it diverges. Persistent uncertainties modeling, the influential pressure strain correlation and dissipation terms. These are very important in low RE flow, but unfortunately, nobody knows what is the best model for these terms, pressure correlation and dissipation terms. Only recently, some PhD work I have seen from IIT Kharagpur by one Odia person, Panda. Yes, I was his examiner. That is a very good mathematical work. He did experiments also. But like that, some 4 or 5 works in the world you can find out. And engineers don't bother. They say, if it works well for the mean standards, why do you worry about pressure strain correlation? Anyway, non-linear eddy viscosity based model. This is also another attempt, potential alternative that use eddy viscosity model, but don't use the linear relationship. Gatsky was famous, he died. Taulby, they did it. All these papers are available everywhere. So I'm not going into the details of that. Go next. Hmm. This is also simply I will show that as you derive the equation, derive is of course too much of claim. It's a show a balance of k, a balance of epsilon. It is possible to find or derive an exact transport equation for Reynolds stress tensor. I mean, you can find out u plus uy, u plus uj, subtract, product, you can find this. But what is the need of this? Nothing, because you see, the problem is we have already got third correlation, ui, uj, uk. We already don't know the second correlation. Then pressure fluctuation correlation. So all these are useless. So what people have done, Rodi has done, Launder, Rees, Rodi, they have taken the convective term, which is of course doable. In the source term, they have assumed some of the drastic assumptions and converted these things into doable, like the tau, the k, these are all measurable, doable. So this model works better. Some of the problems they have shown, but I would still say the ab initio from engineer point of view, people don't use it. It is available. The models are, this model is available in both ANSYS and star CCM plus. So we don't. So these are the turbulence models which I have developed in our code RANS 3D, which I will talk tomorrow. We have K epsilon model, we have K omega model. By choosing the number, you can choose anything. We have the SST, the shear stress transport. We have the Spalart-Almaraz. Spalart is a very, very interesting person. I have met him twice, once in IISc, once in France, in a conference. So Sparlet thinks, see, all that you are doing all this to get what? Mu t, the turbulent eddy viscosity. Then why do you derive this velocity scale, length scale? It is not possible. So he said, don't do that. You write a sort of balance of the mu t equation, which you are calling, I mean, we are calling it turbulent viscosity. And that equation was based on empirical findings. All the results collected, take some constant there. So like that. There is mathematics is very weak here. There is no mathematics. These all observation and chunk of data. And that if you solve, you can put reasonable boundary conditions and you get the mu t, and then you get everything. So his concept was don't use separate equations for k and epsilon. Okay. Then V2F, this was Durbin, with whom I worked for 1 year at NASA. So he thinks the k is a good measure for turbulence. The root over v square. That means if you are considering the turbulence on a plate, what is important is the fluctuation normal to the plate, not this or this, this. So he derived several practical equations for v square bar, and the model equation work well, especially for scalar transport. Heat transfer problem, they work very well. It is available in both models. This just I wanted to show that what is this LES? I'm not showing any result. LES means you keep on making the grid fine, 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 and go up to certain scale where up to which you can go with your money, cash for computation. And then you say that I have resolved all the large eddies. What I have not resolved are the subgrid scale models, which are below the grid. Grid is say this much, but there will be small, small molecules inside this. So what they are doing to turbulence, what they are doing to my momentum transport, I don't know. So what he has done, he has made a spatial average, I mean like this, and subgrid scale is u minus ui bar. Whatever is actual minus whatever the Dyarov's resolved scale filtered velocity. And the filter width is depending on grade. And what he did is continuity is same. Here we are putting the thing here as this. That means the subgrid scales are to be modeled. And ui bar, uij bar is already we are solving, so you get it. So the idea is this one you don't do with this. This one you express some model, some empirical, some other correlation. Then at least you will be sure that the which are the turbulence caused by the larger chunks, larger bubbles are resolved. And smaller than these are not resolved. We are using some empirical correlation. So just for sharing with you, I mean, I'm not giving any details. So what are the concluding remarks? Good, 4:30. Turbulence models are required for estimating because when the flow is turbulent, things are going out of your control because they just move around here and there. So estimating the statistical second moment correlation, that is the Reynolds average Navier-Stokes, right? That's what we do for turbulent flow. And two important parameters are identified, length scale and velocity scale. That means the chunks of the fluid are moving here and there in the form of vortices. And the vortex has a strength, the velocity, and the vortex has a size. The size is decided by the length scale, or let us say the opposite way. The length scale of turbulence decided by the size of the vortex, and velocity scale by the strength of the vortex, the kinetic energy. So the K epsilon model is the widely used, but it is inaccurate for flows with adverse pressure gradient like a diffuser. We know that. K omega model is claimed to be accurate for variable pressure gradient, but its sensitivity to the free stream boundary condition. If you put free stream velocities to infinity, it does create some problem, extra omega, near the free stream. So for the boundary layer, K epsilon is good near the free stream, K omega is good near the wall. That's how the SST has been framed. Sparlet-Almaras is on a single eddy viscosity equation. Well, the aero people, the Boeing and all these aircraft manufacturers, they are happy. because the computation time is less. But I am still doubtful about the arguments he gave to justify that single eddy viscosity is enough. Any two equation model based on the concept of isotropic eddy viscosity. That means at a point it is not dependent on direction, and that is not true. Fails in flow situations where anisotropy in the Reynolds component is significant. Why? Because the mean standard is changing. That depends on the problem. Large eddy simulation involving very fine grained, large number of nodes, expensive, but likely to yield better results for bound layers as well as for recirculating flows because you are resolving the turbulence up to a certain scale. Beyond that, below that, you are doing some empirical. So that is it. I think we can close the presentation because I have already concluded. And I must say that more than this is not required to know to use the CFD turbulence model in CFD. Because turbulence is an open field. There are a lot of vast knowledge, vast things are as yet unexplored. So people are working every day. So we don't have to worry as CFD person, provided the results we are getting required for our engineering purpose is satisfactory. If that is satisfactory, we don't care about details. But if one is interested about the turbulence itself, then one has to go further. This two equation, three equation model are not good enough. I think that's all. Now it is open and we'll see you tomorrow again with the code I have developed for the last several years. Good.
Thank you, sir, for your valuable information today. We have a great session about the turbulent modeling. It's almost a complex modeling, and I think participants have enjoyed your session. I want to take some questions regarding the same. Naveen sir has asked, what is the impact of various models on the convergence of solution?
What is that?
What is the impact of the various models on the convergence of solution?
That is a difficult thing to answer. It is, I would say almost impossible because nobody knows which one is good for what. The only way is to compare it with experimental data. Because nowadays, very good experimental device is there, at least for measurement of, say, turbulent stresses, U dash, B dash bar. So that is the only way to justify your, model. And impact of the models on the convergence of solution, that I would say nobody can answer this. I mean, everybody will say my models are good, but there is no, what should I say, mathematical thing because the models themselves, all the components of the models are empirical. So from that to convert, on the convergence, how it affects, difficult to say. But of course, if you have two equation model, the convergence rate is better than when you have four equation, five equation, like you are solving for U dash, B dash bar, or all the components, Reynolds stress model. Of course, the convergence will take much more. So complexity of the model decides convergence because one should not forget that something is happening and we are trying to make it happen by some estimates in our mathematics. We have no proof that exactly dynamics of this is replaced by this. No, even mixing like model itself, which is used by everybody, there is no proof for it. There is some experimental evidence. That's it. So that is why the empiricism is built in. Okay. Jishnu, Chandran, are the turbulence chunks creating a flow opposition similar to the? No, not always. Turbulence is not always trying to block. Viscosity, of course, is trying to stabilize the flow, whereas The turbulent chunks are to some extent opposite because in some case near the wall it may try to stabilize, even it is turbulent. But in middle of the flow, the turbulent chunks enhances mixing. So we can't say that it is behaving like viscosity, like damping. Viscosity is a very good damper, but turbulence not always. Then CFD, when we assign the for getting solution, how much is it accurate with real turbulence? This is also remains a question mark because how good is your experimental facility? That is first dependent on that because what I will really, believe depending on how good. So if we use any application with a measurement, we have to first see how good, how accurate is the measurement. Exactly like that, even the models also I have to first see because you have seen how the models are modeled in between. So this question is direct answer is not possible. Depends case to case. And going for turbulence model, the first thing one should do is try with the proven model. Proven means maximum number of cases successful, like shear flow, turbulent shear flow. Try that. If that works, then I'll have some confidence and then build it on for the models. So this does not satisfy the question maker always. What is the method to reattachment zone? That is, I think, from the mean velocity profile, it will be a good guess. If the mean velocity profile you see, and on the surface, near the surface, it changes sign. So you can say that reattachment and separation, both. I mean, we do that. But how good it will be in three-dimensional flow, I have no idea. I mean, good. Basic criteria in fluid solid interaction study. Well, that depends on the structure, engineering structure of the case also, where this fluid solid interaction, everything is a fluid solid interaction. But depending on the case, geometrical complexity, flow complexity, I have to choose. I think my suggestion will be try with K epsilon, try with K omega, you get result compare. If both are satisfactorily good, then try SST. Or if you are already known that K epsilon won't work here, try with SST. And SST, most of the cases, because of this combination, it works. And even for transitional flow, I have written the code once again for coupling SST kind of thing, and that works. But it depends on the problem. LES-DS, of course, I will not advise rightly to go to LES. DES also detached steady simulation. That was Pallat's LES. Like Pallat says, whenever there is separation, you start using the LES. But as long as separation has not taken place, you keep your K epsilon, K omega. So usually what happens in DES, near those junction points, there is always a problem, always. I have not experienced much. I have done very few cases where, and in my code, DES is not properly written and included. So I am happy with K omega mostly, or the K omega K epsilon combination with SST. LES is different. LES, of course, I have done. There are a lot of possibilities to get better results. But DES, my experience is very poor. So I can't say. Send links. What link? Can you suggest a good textbook? I will give you a list of books to the organizers. They will share it with you. Tomorrow I'll bring that. I made one. But Wilcox is good, very good if you know Wilcox because it has more or less many ideas. Can you use LES supersonic? Well, in principle, yes, but I cannot help you in saying how. I know that LES work better. Uh, but it all depends on the experiments you do. So first job you have to run with a kind of eddy viscosity model, and then if it works, you can shift from that level to LES. Just like that, from beginning to LES, you may have problem. Which model is good? Solar panel, wind load. I don't know. This all depends on experience. See, telling someone that use this model that will be good is impossible. I mean, I think I will be unjustified. So that injustice I don't want to make, because I will say this model is better. The other man will say, "Arey, have you tried this?" So better not to conclude on that. Good. Where transient information regarding possibility of growth of filtered out radiation cards. I don't know. This is possible. I have heard of this, the growth of filtered out radiation, but because I have no experience, I cannot suggest anything to do that. Once one you have to try to see the whether it is happening or not. The growth of filtered out radiation, right? Filtered out, I think you are meaning by what has been done in the first part when you did not have LES. So yes, LES does filter out, yes, the smaller one. So they can grow. And if they grow to large AD, then you have real problem because you have not considered that. You have considered that I am stopping my large AD only at that level. Below that, there is no chance of growth. But they cannot grow, I cannot confidently say. Because vertical flow is always like that. Damps due to the viscosity, but sometimes they do join and grow. So what is the guarantee? This grid is in your mind. The physically the flow does not have a grid. So it can. And if it grows, you will be in problem. Maybe that will be shown to you as divergence of your part, alias part. You may have to say, okay, I have to make the grid finer and then try. That's the only thing you can do.
So I hope all the participants has given the questions and all
Yeah.
answers has been got in them.
Otherwise, you can send me in
Yes, sir.
writing.
So thank you, sir, for this nice
Okay.
informative session to you. I request again all the participants to switch on the video so that we can capture one video
Capture.
picture. So we will end the session. I also request to give the feedback as per the link given. Please give it.
The people say, hello. Oh, this is Maharashtra. Maharashtra. Cars are all Maharashtra. Cars. Not CA car. Good. Rim shooting. But we are not visible to them. Your video is not on.
Yes, sir. Most of them. Yes, sir. Just a minute, sir. We will have it.
Yeah.
Oh, now you can see.
Hello, sir.
Hello, hello. Good.
So, good evening, everyone.
Yes, tomorrow again.
Thank you for attending the three sessions, the first session, the first day of the activity. And similarly, tomorrow we are going to have another two new resource persons.
Yes. Hopefully they come.
Yeah,
Won't put us into trouble.
those two also will be the more interesting sessions. And we will share all the PPTs because most of the requests we are receiving. Accordingly, we will have a drive. We'll put all the materials. You can use that. you share the link and you can use those PPTs,
He's in the
all
ocean.
the materials, everything. So by today or by tomorrow morning, you can get all those things. We are trying our best. Okay, for that one.
Okay then.
And tomorrow, today 9:30 inaugural session was there. But tomorrow onwards, classes will start at for exactly 10 a.m. So all are advised to join by 9:50 a.m. So that in time we'll start our sessions.
Thank you.
So with them, thank you all. Good evening to all of you.
Good evening.
Thank you, sir. Thank you all for participating.
Near report.
Yes.
Okay, thank you.
Thank you,
session.
sir. Thank you, sir.
You're saying it. I'm not saying anything. Shajit in the ocean. Okay, चल बहुत हुआ आज तो जाने का बाजार को बंद
Thank you, sir.